Where is... Oh. All right, so let's look at this section called an introduction to general polynomial functions. We've already looked at positive integer powers of x, right? So we looked at how to graph those independently, but the question is, what happens when you start adding them together, right? What if I added x to the fourth, x to the cubed, and 2x squared together, and I want to graph that sum? What do you do? All right, and so we're not going to linger forever on the topic because you actually do this more sophisticatedly in the Calc 1. But I do want you to be familiar with kind of what to expect with polynomials in general, just some general rules. All right, so a polynomial function is obtained by adding or subtracting constant multiples of non-negative integer powers of x. So that means like x squared, x cubed, x to the fourth, x to the fifth. No x to the negative powers, no fractional exponents, no square roots, no divisions, just constant number or constant multiples of positive integer powers of x, including just constants. The degree of a polynomial is the highest exponent of any x value that occurs in the polynomial. So once you've written the polynomial in this form, right, so if you had a bunch of factors being multiplied together, you'd literally have to multiply them out to identify the one with the highest power. That power is the degree. All right. Fact 1, since you're just taking positive integer powers of x, multiplying and adding, the domain of any polynomial functions all real numbers. Right, that's a fact for any of them. All right, now using the definition, we want to be able to determine if any of these are polynomials, and if they're not, explain why. All right, and so for the first one, that's a polynomial, right? X to the fifth is fine. 3 is a constant, and I can subtract those. Those are constant multiples of positive integer powers of x being added or subtracted. And so this is a polynomial, and its degree is 5, right? It's the highest exponent that occurs. Okay. This guy is not a polynomial. Okay, so this is not a polynomial because you have a negative power of x in there, right? And so you can only have positive integer powers of x, so that's not. Pi is a constant. Constants are polynomials, right? The integer power of x is 0, and so that's fine. It's a graph is a horizontal line, so that is a polynomial. Oops, that is a polynomial. The degree of any constant is just 0. This guy is not a polynomial because you have a square root term, right? And so the domain of this function, notice, is everything that's non-negative, but the domain of any polynomial is all reals. And so that's no, because the integer, or the power of x that you have here technically is 3/2. That's not an integer. This guy is a polynomial. It's a product of linear factors. To find out what the standard form would be, you literally multiply it out. And so you'd have x squared plus 3x minus 4. That is a second degree polynomial. It's a quadratic. This guy is not a polynomial because you're dividing by x, right? So you have to throw out 0 from the domain, and we know the domain of any polynomial is all reals. All right, so just knowing how to read the definition and what is and isn't a polynomial is important later on. Okay, so fact 2, or I'm labeling it as fact 1 here, but the next fact up of interest is that the graph of a polynomial is always going to be unbroken, so there's never any holes in it, and there are never any sharp corners, right? And so you won't have anything that looks like this, or even a hole like that. That won't happen. You won't have any sharp corners like this, okay? These, again, are facts that you prove later, right? This deals with continuity and differentiability in the Calc 1. But for now, we're going to assume that these sorts of phenomena will not happen. This is just terminology, right? And so we know that if you were to factor an expression, the product of the two expressions you get as a result, 2 or 3 even, are called factors, right? The process of factoring is to write a complicated expression as a product of simpler ones, and the expressions that you are computing the product of are called factors of the original. Linked to those are the zeros of the original function, right? So any value that makes the factor 0 is called a zero of the function, naturally enough. And then in terms of intercepts, each real zero corresponds to an x-intercept of the graph of that function. Right, so just 3 things that really give you the same information, but they're different terminology for stating that. All right, so let's look at example 2. You want to find the x-intercepts of this function. Well, an x-intercept occurs when the y value is 0. The only way that this expression can be 0 is if either of the factors is 0, right? And the 0 of the factors are what make it 0, right? So x equals 9 or x equals minus 2 would be the zeros of this function, and they give rise to the x-intercepts as such. Right. Now you don't have to just have a product of 2 factors. You can have a product of 3 factors or 1,700 factors. It doesn't matter, right? So if I have a product of these factors, each one equals 0. If you set each one equal to 0, you'll find a new intercept, and that's what we do here. Set each one equal to 0. If you solve those for x, you get these solutions respectively, and each of those 3 gives you a x-intercept of the graph of this function. Okay. Later on, you'll be able to see how to actually get the graph, but you'll notice that in fact it crosses at 3 points. All right, so you go ahead and try these. Find the x-intercepts of these functions, and keep in mind that an x-intercept must be a real number, not an imaginary one. Okay, so if you look at the first one, these are both already factored, more or less. And so here, for the first one, you have a product of 3 expressions. This guy is linear, so it doesn't factor any further. This is a sum of squares, and so does not factor. This one does factor into a product of simpler ones. It's a difference of squares, so that factors at x minus 3 times x plus 3. Okay. If you set each of these equal to 0, the first one gives you minus 2, that gives you 3, and this one gives you negative 3. But setting this guy equal to 0 does not yield any real solutions, right? You'd have x squared equals negative 2, and so you'd get plus or minus I radical 2. Those are not x-intercepts, right? So you exclude any imaginary solutions from consideration when asking about x-intercepts of a graph. All right, so each of these gives you an x-intercept. Here, same sort of phenomenon occurs. You set each of these equal to 0. Well, certainly x squared is 0 when x is 0, but this guy is never 0. It's a sum of squares. And so you only have one x-intercept this time, namely when x is 0. All right. This is what I was saying in terms of just interchanging the terminology. An x-intercept of a function is a point a0, right, on the graph. But that'll happen if you plug in a for the x and you get 0 out, right? So we'll call a 0 of p of x a number so that if you plug it in, you get 0 out. Okay? Means exactly the same thing as an x-intercept, just a different way of phrasing it. And then here, a factor of a polynomial is another function that when you multiply it by some other polynomial, you get it back. So just think of this as a factor of any polynomial is a expression that if you multiply by a simpler one, you get back the original. All right. The big connection that we want here is that if you have a 0 of a function, then you also have a factor, right? So for instance here, if you look at this guy, we know that negative 5 halves is a 0 of p of x, makes that guy 0. So x minus it is a factor. So x plus 5 halves is a factor of this polynomial. That'll be very helpful later when you're trying to write a polynomial as a product of simpler things and the original degree is bigger than 2. right? If it's quadratic, you know how to handle all of those. Either you factor it or you use the quadratic formula. The minute it's cubed, that's not really true in general. And so this will be very helpful for those instances. All right. So let's, well, I already had the Ortern solution. Let's talk about it. So this, again, is just a final sort of comment on that terminology. All right, so you have a polynomial p of x, and you want to know which of those is not equivalent to the others. All right, so minus 1, 0 is an x-intercept of the graph of p of x. The only way that would happen is if you plugged -1 in for x and got 0 as an output. What that means is that p of -1 is 0, right? So a and d are equivalent. Okay. Now, let's compare these two guys, right? If x equals -1 is a 0 of p of x, it means that if you plug it in for x, you get 0 out, right? So c means the same thing as d. If you plug in -1 for x, you get a 0 as an output. So it must be b is the outlier here. And why? Well, let's think about it. If -1 is a 0, then x minus a -1 is a factor, but x minus a -1 is x plus 1, not x minus 1. So b is the one that's wrong, right? In order for these all to have been equivalent, you would have had x plus 1 here as a factor. That would have been true. Okay, so hopefully the terminology makes a little bit more sense to you. What I want to do now is talk about the nature of what the graph looks like near the x-intercepts, right? If we have the polynomial factored or we can factor it easily, then the easiest points to get are the ones that make it 0, right? And if it's in factored form, you just set the factors equal to 0, right? So I know where it crosses the x-axis. What I would like to know is how it crosses. Does it go through it? Does it look like a U by it, or does it swoop down like x cubed? It would be nice to know so that I can gain some insight into the graph of that function nearby. To that end, the way the graph looks at an x-intercept is directly linked to its multiplicity. All right, so what does that mean? The multiplicity of a 0 is the degree to which the factor x minus a is raised. And so what does that mean? Well, let's look at this product here. This is a polynomial. Notice the degree of the polynomial would be 8, because if I were to multiply all this out, this would yield a 5th degree polynomial, a 2nd, and a 1st. If I multiply all that out, I wouldn't want to, but if I did, the highest power of x that would occur would have been 8. All right, notice here that the multiplicity of 3, so 3 is the 0 for the corresponding to this factor. Its multiplicity is 1 because the exponent to which x minus 3 is raised is 1. Okay, simple. -4 is this 0. Remember, it's what makes the factor equal to 0 is the 0 that I'm talking about, right? This 0, -4, has a multiplicity of 2 because its corresponding factor is being raised to the 2nd power. Okay, and then finally, -1 has a multiplicity of 5 because its factor is raised to the 5th power. Okay, here these two facts are actually quite useful. All right, so if a is equal to, let's see, that's not true. So let a be a 0 if the multiplicity is 1. So if multiplicity of a is 1, then it crosses linearly, right? So make that change in your PDF or on it. Right, so the actual 0 itself is irrelevant. It's the multiplicity that's important. Okay. And so here, if the multiplicity is 1, it's just going to go straight down through the graph from one side to the other, just like this. Okay. If the multiplicity is odd, it's going to look like the cubic. It's still going to go through, but it's going to do so kind of in a nice cubic way. Okay, so multiplicity of 1, boom, straight through like a line. Odd multiplicity, 3, 5, 7, it's going to swoop through tangentially, like these. If it has an even multiplicity, then it's going to be tangent. So it's going to look like a parabola on one side or the other. Okay, those are facts that you have to have more information about derivatives to actually prove. So we're just using them as fact. All right, Let's look at example 6 using them. So I want to determine the zeros and multiplicity of for this polynomial function. All right. So here, there are 2 zeros, or it's already factored, so we don't have to worry about doing that. The zeros are linked to each of these factors. The 0 for this guy is 0. Its multiplicity is 3, which is odd. And so we know that the graph crosses the x-axis tangentially, right? It's going to swoop down like x cubed. The 0 corresponding to this guy is 2, and its multiplicity is 2. Right? And so we know that since the multiplicity is even, it's going to be tangent to the x-axis, like one of these. We don't know on which side. I'm not worried about that at this point. We just know that it's going to either look like this or like this at 2. Okay. Go ahead and do the same sort of thing. This is going to be redundant after a while, but that's okay. Go ahead and find the zeros for each of these guys, right? And then classify them according to the multiplicity, just to kind of generally say what the graph would generally look like. Either it's linear through the axis, tangential like x cubed, or parabolic like x squared. And then actually find the degree of the polynomial. Okay. All right, so do that, pause the video, do it, and then we'll talk about that. All right, let's look at the first one. So first off, to find the degree of a polynomial that's already factored, basically all you have to do is look at the degree or the multiplicities of all of the zeros and add them up, right? So the reason for that is the following. If I were to cube this, right, this is a linear factor already. So if I were to cube it, I'd get a cubic graph. If I squared this one, I'd get a quadratic. That's already linear and that's already cubed. If I were to multiply the biggest power terms of all those pieces together, the biggest power that I would ever get would be one where I simply added the powers of all of those up. So I get x cubed first, second, and third. I would have a 9th degree polynomial in the end. If you don't believe me, you can multiply it out to see. But generally, you just want to find the biggest power term for every one of these factors and then add those powers up. All right, the zeros, you just set each factor equal to 0 and solve for x. So the factors are 0, -1, 5/2, and -4/3. The multiplicities are the powers of those factors in each case. The two with the odd powers of 3 are tangential to the x-axis and cross through it. This linear factor, it just crosses through. And this quadratic looks like a parabola. So it's tangent to it and stays on one side. That's as simple as that. That's all you have to do. Each of these guys here is a squared linear factor. So the degree of the whole thing would be 2 + 2 + 2, which is 6. Each one, so the zeros are what make the inside 0, namely -2/3, -4/3, and -7/3. And each of those has a multiplicity of 2. So each of those will look like x squared, just a parabola on one side of the x-axis. And that side actually turns out to be the positive side, since everything here, you're multiplying 3 positive numbers no matter what, right? So it always will be up on the x-axis. This one's trickier because I didn't fully factor it for you. And so here notice that you cannot factor x squared + 4 further, right? That is irreducible, not factorable quadratic. This guy factors as x - 3 times x + 3. And the inside of this guy factors as x + 2 times x + 1. Each of those will then have a power of 2. And so here, look at the factored form. What you want to do now to find the degree is go here. Each of these guys is linear. This one's not. So if you were to square this one, you'd have a power of 2, another power of 2. Each of these contributes a power of 1, and this one has a power of 2 already in it, right? And so the degree would be 2 + 1 + 1 + 2 + 2. That'll give you 8 in the end. Okay. Now here, there's no 0 to classify, so you don't bother with that. But there are 4 real zeros from these other terms. -3 and 3 both have a multiplicity of 1, so it crosses the x-axis like a line. both -2 and -1 have a multiplicity of 2, so it crosses like a quadratic, or sorry, it's tangent to the x-axis like a quadratic. Okay, next the next topic related to polynomials are the turning points. And a turning point is how it actually crosses, or how it changes from increasing to decreasing, right? So if we go from, all right, go outside, take that off outside. All right, so if you actually go from decreasing to increasing or vice versa, at some point you're going to have a local min or a max. It's going to change at that point. So that would be a turning point. That would be a turning point as with this. Okay. Okay. So the question is, how many turning points can a polynomial have, and how do you find them? Right. And so I'm not going to spend too much time on this, but notice here that you can have a turning point one between two x-intercepts, right? So you could have one here, you could have one there, and have one there, but beyond that you can't, because the minute you have another turning point, it has to cross again, right? So there's a direct link between how many zeros a polynomial can have and how many turning points it could have. If a polynomial had a degree of n and it factored in terms of n distinct linear factors, then it's going to have n x-intercepts, right? But we know that you can only have a turning point between two x-intercepts, so there could be at most n-1 turning points. That's something that you'd have to really piddle around with particular values of n, right? So it's not easy at all to prove that, but it is a fact. All right, so I'm going to look down here at fact 4. A polynomial of degree n can have at most n-1 turning points. Okay. All right, long-term behavior. So here, what I want to do is we looked at what happens at and between x-intercepts. That tells you what happens close by to the origin. The question now is what happens for beyond that, to the left and to the right, right? So once you've found all your x-intercepts, I need to know what the graph is going to do then going forward. And so let's look at this function. We have a cubic graph, and I want to know what that graph looks like for x very large. All right, and so what I'm going to do is I'm going to factor out the term of highest degree from all three terms. So I'm going to yank the x cubed out. And what that's going to enable me to do, looks odd, but what it enables me to do is the following. The minute you yank that at the highest power term out, then in this expression, the first term is always going to be 1. Right, and that's not going to change with whatever x values you consider. Okay, if you yank an x cubed out of 3x, what that means is what do you multiply x cubed by to get negative 3x? Well, you would multiply by negative 3 over x squared, right? And so it's not factoring in the sense that you're getting a simpler expression. Rather, you're getting an expression that's going to algebraically help me make the observation that I want, right? But the way you think about it is, what do I multiply this guy by to get that guy? Okay? Same way here, what do I multiply x cubed by to get 1? I multiply by 1 over x cubed. All right? And so now I've managed to just rewrite my polynomial as that product. Right? The question is, remember, we want to know what happens to this polynomial for x very, very large in either direction. And so what we'll do is rewrite this. Here, I'll just pause this. Okay, so now notice that as x gets large, this value, if you just literally put in values that are larger and larger for x, 10, 100, 1,000, 1,000,000, if you were to compute those in a calculator, what you'll notice is that these terms here become negligibly small. And so they have no impact eventually on the graph of p of x, right? They become 0 essentially. And so that what that means is that for x very, very large, the graph of p of x really just looks like x cubed, right? Because you're multiplying it by 1 basically. And so what you're saying is that for x large in either direction, that's why I'm using absolute value of x, it can be very negative or very positive, doesn't matter. These fractions are very, very close to 0. And so that the graph of p of x behaves basically like its leading term, its x cubed term. All right. I've left you some blanks here, so you can actually try this on your own. But what you want, if you are so inclined to do so, here what you want to do is yank a negative x to the fourth out, right, and go through this process to see that you'll get the same thing, right? You'll have negative x to the fourth times a quantity of 1 and then plus or minus a bunch of fractions where you have an x in the bottom, okay? Same way here for the x to the fifth. In so doing, we're going to make the following conclusion. The graph of a nth degree polynomial, so I give you any polynomial I want, its leading coefficient is the term of highest degree, okay? Basically, its graph is going to look like the graph of its leading coefficient for x very, very large, okay? Thing is, we know what those graphs look like. Those are constant multiples of either an even positive integer or an odd positive integer power, right? And so we know exactly what those graphs look like, right? If the number, so if the coefficient here, the a sub n, if that number is positive and n is even, it looks like a parabola. It opens up. So as x gets big, the tail ends of the polynomial both go up to plus infinity. If a is positive and n is odd, then he goes up to the right and down to the left. The exact opposite happens for a negative because that involves a reflection of this graph over the x-axis, right? And so it goes down to minus infinity for both, or up to the left and down to the right. Okay. All right, so let's look at this, for example. What does the graph of the polynomial function, this guy, look like for x large in both directions? Well, what we know is that the leading coefficient is the term of highest degree, which is your minus 5x cubed. That graph is of this sort. It's a negative a with an odd multiplicity. And so we know that as x goes to minus infinity, it goes to plus infinity. And as x moves to the right, it goes down to minus infinity. Right? So it tells you what happens in the tails, basically, for x very, very large in either direction. All right. Try this your term, right? So here you want to find, basically you have to find what the term of highest degree would be in each of these cases. You need the actual term, not just the degree, because the coefficient being positive or negative actually has an impact. And then use our results to classify the long-term behavior. Let's see what happens. All right, so let's look at the first one. If you were to multiply this out, let's actually track what happens to the actual biggest term. You have a negative x times an x, technically times a 9x squared and an x cubed, right? So you have, actually this is not correct. This should be 9x squared. All right, and so this is not correct. We will correct that one. All right, good thing we talked about this one. All right, so notice here, you'll have a negative 9x to the 7th as your leading term. That's of the form of this guy, a negative and an odd power of x. And so what you'll get is it opens as x goes to the left, it goes up. The polynomial goes up to plus infinity. And as x goes to the right, the polynomial's graph goes down to minus infinity. Right, the graph in the tail behaves just like the graph of that guy does. For number 2, this one's fine. The leading coefficient in each of these is 4x squared. So if I multiply 4x squared times itself 3 times, I do get 64x to the 6th. That's a positive multiple of an even power. So it's going to look like x squared. It's going to go up to plus infinity as x goes in either direction. Okay, and then the same sort of thing here as it was above. All right. I'm going to omit example 8 and also your turn 5, just out of interest of time. You're going to learn how to graph these very carefully when you take Calc 1. if you're interested to kind of see how it all fits together now, absolutely work through these, but I won't require you to do it for homework or for the exam. But it is an interesting sort of how do you pull it together sort of problem. Okay, so you can view that on your own. In the homework, we're just going to omit number 7, right? So hopefully you're watching this video. Don't worry about number 7. I'm not going to have you responsible for that. All the other ones you should be able to do with what we've talked about. All right, so give it a go and let me know how it goes. All right, bye.